Today, I'll be talking about stellar kinematic spiral structure in the Milky Way. This work is based on my honours project I did last year at the University of Sydney, supervised by Joss Bland-Hawthorne. So since the early 1800s, there have been observations of spiral galaxies. And in more recent decades, they have been studied in the gas phase, but their nature, origin, and long-lasting stability remains elusive. In light of the ESA Gaia satellite, however, for the first time, we are able to reveal spiral structure in stars and clarify some of these ambiguities. The second Gaia release has provided accurate 6D phase space coordinates for over 6 million stars, with over 35 million anticipated in the third data release later this year. Some notable works include, but are not limited to, Antoja's 2018 paper on phase space spirals, Eiler's 2020 paper on kinematic spiral structure in mean radial velocities, and Poggio's 2021 paper on stellar overdensities. So how does our kinematic data help us to trace spiral arms? Well, this is owed to the density wave theory, first devised by Lin and Xu. Can you see my cursor? Yeah, okay. And that's the most commonly adopted model of spiral arm rotation. The bold black line shown here represents the density wave pattern, which moves at omega p. Outside co-rotation and due to the flat rotation curve of the Milky Way, stars and rotating gas travel at speeds slower than this density wave pattern. And as a result, as shown by these arrows, the density wave catches up to the gas, compresses it, and then forms these young blue stars, which later get left behind. And as the population ages, it'll diffuse and form an even tighter pitch angle as marked by this red line. Conversely, within co-rotation, we have the opposite effect because the stars themselves move faster. So the gas approaches the density wave itself from behind, and upon compression will form these young stars, which then move further and further away as they age. So how does this, again, impact our kinematics? Well, depending on the star's position relative to the density wave, stars will either increase or decrease their radial velocity to move into the density wave, since it is a potential well. So here is a schematic diagram demonstrating this. The red and blue lines are concentric circles. The stars at smaller radii will move outwards to fall into the spiral potential well, leading to an increase in radial velocity. And stars on the outside of this density wave will move inwards, which leads to a decrease in radial velocity. So basically, we get this red-blue gradient of radial velocities with increasing radius, where the line between red and blue can be used to trace the location of our density wave and thus our spiral arms. So alongside stellar data from Gaia, which I cross-matched with other surveys, including Apogee and 2MASS, I compared observational results to data of an N-body simulation presented in Bland-Hawthorne and Tepa-Garcia, which models the kinematics and dynamics of a stellar disk perturbed by a dwarf galaxy, or the impact of a dwarf galaxy, rather. The disk is impacted by a small mass at 100 megayears and is left to evolve for 2 gigayears. The 4 main variations of the model that I considered are shown here. The first is just a simple disk with no central bar, and it has an impact at 20 kiloparsecs out from the galactic center. The following 3 models contain a central bar where one has no impact and the other 2 are impacted at 2 different distances from the galactic center. So now let's look at the sample of stars I used to reveal the spiral structure. So my sample selection was based on the work of Eiler's in her 2020 paper. So to select these stars, I cross-matched Gaia with 2MASS and Apogee. Distances to stars were obtained by inverting parallaxes whose values were weighted by both Gaia and apogee. I used galactocentric velocities from apogee calculated using the ASTRO NN deep learning code. And then I also just performed the following cuts to leave us with roughly 150,000 upper red giant branch stars. And these are my results. So on the left-hand side, we have the observational data, and we are plotting the mean galactocentric radial velocity. So here we're looking at the XY plane, so the galactic disk from above, essentially. To plot this, I gridded... I cut up the grid in 0.25 kiloparsec squares, and then took the mean radial velocity in each of these grid squares and smoothed it with a Gaussian kernel to better reveal the spiral structure. Remember, wherever we see a red-blue gradient, we can trace a spiral arm. So we can see one here and potentially one here, although we don't have too much data. Now, positive values, which are shown in red, as per my schematic diagram, represent stars moving away from the galactic center, which is at the origin. And negative values shown in blue represent stars moving towards the galactic center. And the sun is marked here at about 8.2 kiloparsecs. Now, the right-hand side velocity plot arises from a two-armed logarithmic spiral whose parameters were fit to the data using Monte Carlo methods. I emitted radii less than 5 kiloparsecs as this region was dominated by the bulge, so we have a different perturbing potential. I also computed the residual map to compare the data to the toy model and the distribution shown on the right. So we can see it matches up relatively well. A few outstanding points on the outskirts, but that's due to apogee potentially having less accurate measurements away from the sun, and a small island here to the left. Although if we look back at our plot, that is roughly at the interface between positive and negative radial velocities. So yes.
You've got 2 more minutes.
No worries. So possibly through the smoothing via the Gaussian kernel, this may have diffused some of the kinematic structure. Finally, this is my comparison of the data, which is in the middle column, to each of the mean radial velocity plots on the left-hand side with the keys described in the table here. And we have a histogram on the far right for each plot in each row. So we can see the simple disk with no impact has arms generated that are way too thin, so we can rule that out. The bar disk with no impact has the strength of the arms is too weak, and that's shown by the much narrower spread histogram, so we can rule that out, which then leaves us with the bar disk with near and far impact. So the far impact model has the best fit to the histogram, although point-wise, the agreement is much better with the near impact model, as we can see with these two red and blue streams, I guess. It should be noted, though, that our data contains only red giant branch stars, which are much older and redder, and they form more diffused arms with tighter pitch angles as per the density wave theory. However, our models do not account for star formation and the aging of stars, so that should be kept in mind. So to summarize, we investigated the density wave theory of spiral arm structure, and I used an observational data sample of upper red giant branch stars to plot mean radial velocities, and that was also in agreement with a two-armed logarithmic spiral toy model. Moreover, I compared my observational data to an n-body simulation of a stellar disk perturbed by the impact of a dwarf galaxy. We did find a best fit to the bar disk models with either near or far impact, although I think it's not until this model incorporates gas and can thus model star formation that we will be able to have more accurate or informative comparisons to our observations. So what can we infer from all this? Based on our density wave theory, different components of the Milky Way trace the spiral arms in different ways. So essentially our spiral arms have layers. I also studied over densities of younger populations of stars, like the upper main sequence, which I didn't discuss here, but their distribution did agree with the density wave theory. Thank you.